Good morning, everyone. My name is TSS Nagapavan Kumar, and welcome to today's lecture. Today, our topic is CMOS design by using mentor graphics tools. In this session, we will see the CMOS designing process hands-on session by using mentor graphics tools. So, this is the part 1 video. Right. For designing of the CMOS by using Mentor Graphics tool, we are using Mentor Graphics VLSI HEP1 backend tools. HEP1 backend tools, where HEP1 stands for Higher Education Program 1, and this is the backend tools we are using for the CMOS designing process. So in this software, mainly we are using 5 tools. The first one, Pixis schematic tool. By using the schematic tool, we are constructing the schematics and we are generating the symbols. Second one, Pixis layout tools. So this is the tool we are using for constructing the layout diagrams of different types of logical functions by using CMOS logic. Next, third one, ELDO tool. This ELDO tool is a SPICE circuit simulation simulation tool. This is we are using for simulating the schematic diagram which we have drawn by using Pixis schematic tool, right? And fourth one, EZ wave tool. So this is the tool which is we are using for observing the simulation results. So this is a viewer which is viewing the simulation results. And last one, this is the very most and powerful tool in the Mentor Graphics Calibri. So this is the Calibri tool we are using for physical verification. This will do the DRC process, LVS process, and PEX extraction process. These all processes are introducing by this Calibri tool. With that, with these 5 tools, we are doing the CMOS designing process. Let us see actually what we are doing. So the first step, we are drawing the schematics. We are drawing the schematics of the different types of CMOS logical functions. For example, in this picture, we are showing CMOS inverter. CMOS inverter. This is the schematic diagram of CMOS inverter sample view, what we are going to implementing in the Pixis schematic tool. So see here in our top, here we have Pixis schematic tool. In this tool, we are drawing the CMOS logic of CMOS inverter. Okay. So this is the first step. Coming to that second step. So for that schematic diagram, we are generating the inverter symbol. So this is the inverter symbol. This is the inverter symbol we are drawing for the given schematic. So this is the second step. Now coming to that third step. Okay, this is the second step, symbol creation. Third step, whichever the symbol we created, that symbol we are simulating. We are performing the simulation operation. So here input side we are giving logic zeros and ones, and what is the output we are observing by using ELDO and EZ wave tools. So in the second step, we are constructing or we are performing the simulation. After constructing the simulation circuit, next coming to that fourth step, we have to use ELDO tool, and after that we have to see the output waveforms by using DC analysis or AC analysis of EZ wave tool. So see here the EZ wave tool, here we have written here, sorry, we have not written here we can see the EZ wave tool. Okay, right. So by using this EZ wave tool, we can see the DC analysis, and next one, transient analysis. These 2 analysis we are doing by using EZ wave, DC analysis, transient analysis for the digital circuits. If you have any analog circuit, we can see the AC analysis also. We have different variety of analysis parts available that we will see in the coming lecture. Okay, next, coming to that last step, draw the layout diagram. So in the 5th step, we are drawing the layout diagram, and after that, after completion of the drawing the layout, then we will see how to do the DRC process. DRC is nothing but as design rule checker, and LVS, layout versus schematic, and parasitic extraction of capacitances and resistance. This is the last step we are using in this layout designing process. After that, we are generating the GDS2 file creation. In our videos, we are concentrating on these 5 steps. Actually, here we have basically 5 steps. In the first step, we can see the design of the schematic in Pixis schematic, and here we are doing the symbol creation also. That is the first step, designing the schematic in Pixis schematic, and we are drawing the generating the symbols, and we are simulating the whichever the schematic we have designed by using Pixis schematic tool. These 3 operations we are doing in the first tool, Pixis schematic tool. And second tool, after completion of the drawing the schematics, we have to use Eldo software, Eldo tool. We have to use Eldo tool for simulating the schematic environment. Whichever the schematic environment we created, that environment we are simulating by using Eldo tool or AMS tool. Okay, so when you are buying this Mentor graphics tools, you can ask, I want Eldo tool. Otherwise, I want AMS tool. Otherwise, if you want, they will provide you 2 simulation tools for you. Okay, now coming to that third step. In this third step, physical design we are doing, that is layout diagrams we are drawing by using Pixis layout. So the process of drawing the layout diagrams and verifying the functionalities, this is completely we are calling as physical design. So that physical design we are doing by using Pixis layout operations. And coming to that 5th one. In the 5th one, we are performing the physical verifications by using Calibri tool. In this Calibri tool, we are doing the operations such as design rule checking DRC, layout versus schematic, that is LVS operation, and the last one PEX, parasitic extractions of resistances and capacitances. This is the 4th tool here we have. And the last one, back addition of parasitics into schematic for post layout simulation. So after completion of drawing the layouts and verification by using Calibri, we are doing the post layout simulation process. These are the 5 steps here we have generally. So without making any delay, let us enter into our Mentor graphics tools. So this is we are running this Mentor graphics tools by using Linux operating system. This is the Red Hat Linux 6. So now click on the terminal. First click on this terminal. So after clicking on this terminal, we will get a white screen window. Here first you have to type the instruction CSH. That is, we are evoking that C shell window in the Linux environment. So after evoking the C shell, then we have to enter our software address. Okay, so here we have the software address source. Next, forward slash, we have to, this is the source we have to give, whichever the source we are giving. First you have to use the keyword as a source, then you have to type the address. That is the address in my system. The software is available in this location, that is home, software, Mentor graphics, CSHRC, AMS 2009 .cshrc. So first directory home, second directory, in the home directory I have the software, one more directory. In the software directory I have Mentor graphics directory. In that directory I have CSHRC directory. In that CSHRC director I have AMS underscore 2009 .cshrc. This is my location. Now click on the enter. Right. Now I got a message called Mentor graphics tool setup is successful. This is the third, this is the message we are getting after giving the path. Now we have to open our design manager. For that, the shortcut button, the instruction is DMGR underscore IC space ampersand. Now you have to enter. After writing the instruction DMGR underscore IC ampersand, you have to enter. So after you are giving the enter, you will get a project navigator. You have a project navigator. So this is the project navigator. This is the project navigator. So when the project navigator is opened, you have to see previous projects are already available. So give the right click on this previous project and give the close hierarchy. Don't delete. If you delete the previous the person did their project completely erased if you use the delete button. So now you have to use close hierarchy. So we are just closing, right? The appearance we are closed the previous project. Now you are free to start your project. Let us enter into the starting the creation of a project. So first go to the file and click on new and go to the project. File, new project. This is the first step. Click on this project. Now here first you have to enter the project path. So see here, first you have to enter the project path. In this project path, you have to click this browse button. Okay, so here where I am creating my projects, so I am going back and first I have gone to the root directory and I am clicking on this home button and here I am creating a folder. For example, YT12. I have created one folder called YT12. So I'm creating in this, I opened this folder. Now I am in the location at the location of home YT12. So here I'm creating inverter project, that is CMOS inverter. In this video, I am explaining the CMOS inverter schematic drawing and simulation. Okay, so CMOS designing by using inverter. Now click on OK. So see here, my project path is /home. That is a home directory, and Y212 is another directory. In this place, I am creating CMOS inverter. Right. This is the first step. Second step, library creation. Second step, library creation. In this library creation, what we have to do here? We have to call the library files. So see here, nothing is data available in this location. See here, in this location, nothing data is available. Now we have to call the library file. So in the library path, here browse button is there. Click on this browse button and go to first home. Okay, so home, this is the home, and next open the software. Next go to the Mentor Graphics. Now click on here Foundry. Okay, so in the home software, Mentor Graphics, Foundry. Next click on this GDK and Pixis SPT and reflips, IC reflips. Next tech clips. Next generic 13. So this is our library file. Here you have to select the generic 13 library file. So this generic library 13 file path consisting of this one. Okay. So if you want to see again, you have to replay. Otherwise, I will show here. Right here, home software, right? So this is the home folder, software, Mentor Graphics, Foundry, GDK, Pixis SPT HEP, IC reflips, tech clips, generic 13. You select this generic 13 and click on OK. So see here, different types of SGL, LVS, GRC, PEX, all the rules which are available in this generic 13, these all came here. Now click on OK. So here the configuration file is generic 13 and this is the library path and we have fixed the project path. Now click on OK. So when you are clicking on OK, it is asking you want to install any you want to manage any external or logic libraries. Here you have to click add standard libraries. So some two standard libraries are added here. If you want any extra libraries, you click here the browse button. You can add your some more library files also here by using this browse button. Here I'm just adding 2 library files and I'm clicking on OK. right? So I clicked here, okay. Now see here, this is my project name. This is very important. Project Navigator is very important. You have to analyze what is the structure. So CMOS inverter, here option is available. Now here we have two standard libraries. These two are the standard libraries. In this library, what are the components are available? In this library, what are the components are available? You can see here in the object window. So this is the library object window. In this, what are the subcomponents are available? These are the different types of cells here we have. And the last one, generic 13. Right, in this generic 13, here we have the sub cells, okay, sub library components. For example, see here, symbols option is there. In the symbols, double click. Okay, in this symbols, here we have PMOS type, NMOS type, or any other different types of tools are available. Here, when you are creating your CMOS logics, you have to bring your CMOS, NMOS symbols from here. Okay, so this is the library generic 13. Okay, so now we have to enter into our project creation. Now I want to create a schematic diagram in this project. So in this project, you cannot create directly any schematics. So see here, give the right click on this project. So I'm clicked on right click on this and go to the new. So see here, new. What is there? Library is there. So in your project, directly you can create library only. You can't create anything. So click on this library. Now type here CMOS inverter. Okay, so this is very lengthy word. So I'm using INV. Okay, so this is the name I have used for creating CMOS inverter. So I'm clicking on OK. Now see here, under CMOS inverter project. This is my project title, and this project I have a library. So I have this library. This is the library just now we created. So for that reason, in this library, nothing is available. Okay. Now click on give the right click on this library file. Now click on this inverter. Now go to the new. Now go to here schematic. In the library, you can create cells, categories, or component sets. Okay, so in the library, you have to create these three. Under these cells, you can create the schematic. Otherwise, you can click on directly schematic. It will ask what are the parameters required. So I'm clicking on the new schematic. So what it is asking, schematic name, cell name. You have to give this two. Okay, so I'm creating a cell name called inverter. Okay, inverter. First, I want to create the basic schematic for the creation of the symbol purpose. So I am writing here, inverter symbol. This is my cell name. Okay, the same name I am giving for the schematic also. For the schematic also. Okay, right? Cell name I have given inverter sim. Schematic name also I have given inverter underscore sim. Inverter underscore sim. Okay, SYM, symbol, for symbol creation. First I'm creating the symbol, then I will do the simulation process. Okay, so now click on the OK. Right, now this is the Pixis schematic tool for creation of our schematic, for our CMOS schematic. Here we are creating an inverter, CMOS based inverter. For that, this is a schematic tool. Okay, so this is the window. Now here you have to, here the actual process will start here. Actual process will start here. Okay, right. Now coming to here, first you have to see whatever the circuit required. First you have to draw in your notebook and come to here. Right, I know the CMOS inverter. So first click on this add instance button. So see here, add instance button, you can click here. Okay, so you will get a file browser. You have one more shortcut key. You close this one and from your keyboard, just press I button. Okay, now I am pressing the I button from my keyboard. So the same file browser window I got here. Okay, from this, select this generic 13. In this generic 13, just now I said that symbols folder is there. Double click on the symbol folder. Now here you have PMOS and NMOS symbols. Now click on this PMOS symbol and click OK. So place your PMOS component. So I need only one component. So now I'm pressing escape button. Okay. Now I want one more symbol, NMOS. So click on this NMOS symbol and click on OK. Okay, right. So I have placed this NMOS symbol. Right. Now I am scrolling my ring button in my mouse. Okay. So if I scrolled here, so see here what happened. My images are going back, that is zooming out. So when you are using your mouse, in this mouse you have a scroll button. When you are scrolling this button, it will goes back. Okay, now you have to, now you want to zoom, you can zoom, but your components are not available here. When you are scrolling your mouse button, your components are not visible here. Then what you have to do? So then you have to see view all button. So zoom plus, zoom minus, and selected zoom area and view all button. So click on this view all button. For this shortcut is F. Okay, you can use F button. Otherwise, you can click here view all button. Then whichever, wherever the components are available, those will be those will, you can see clearly here. So these are the two major components we required. Then you have to create a VDD terminal and ground terminal, and you have to place here input terminal, output terminal. So see here in the left sided window, right? In this window, we have the add port in option here, add port in option. So click here. This small arrow, you click here, and add port in option is there. Click on this add port in and click here. Input port we got here. We have only one input port, and click here for output port. So click here output port. So we got one output port. So one input port we have taken and one output port also here we have taken. Now we have to take VDD and ground parts. So for VDD and ground parts, you go to the library in the right side. So this is the session window. In this session window, here we have library. Click on this library button. Okay, then click on this 5 libraries are available: IC library, device library, generic library, sources library, macro library. Here VDD and grounds are there in the generic library. Click here generic library. In this generic library, we have a lot of options. From here you can take VDD. So see here, this is the VDD symbol. So click on this and come this your mouse pointer to here and place here. Just give only one time. So here we have one VDD terminal, and take the ground symbol also and bring that ground symbol to here. So I have placed the ground symbol here. So all the components I got here. Now again I am clicking on the click view all button. So this is the these are the maximum components I required here. And in this generic library I am coming back, right? So these are the components you required. Now you have to connect all these components by using wires. So now see here, one wire button is already available. So see this is the wire button. Okay, add wire button option is there. Otherwise you can use a shortcut button W. Okay, I'm clicking W here. So click on this W and click here first one. Here I have clicked only once. Wherever the turning you required, so click here and click here, and at the place of end you have to double click. So see here, it's very simple. At the starting place you have to give the single click, and wherever you want to turn this wire, you have to click at the only single click at the turning place required, and you have to give two double click at the place of end. So see here again, from this base of the from the gate of the NMOS, I'm clicking only once, and at this place I want to turn here, and I want to end my design here. I want to end my wire here. So give that double click here. So I have made double click. Okay. So when you are pressed wire add wire, the mouse pointer, it is showing a plus symbol for identifying the correct location. Okay. So for that reason, this plus symbol came with the mouse. Now go to here, click here once time here, double click at the place of end. So now at the output terminal, click a single click here, and here you have to double click. Now here single click, and I want to give this substrate correction like this, right? So single click, double click, single click, and double click, single click, double click. So all the connections I made. Now press escape button to remove wire from your mouse. So I pressed escape. Now the wire is removed. Anywhere click here for deselecting these wires. Otherwise you can use shortcut F2. Okay, here when you are pressing F2, these items will be deselected. So see here, I am using this F2 button. Okay, I'm clicking here and I am using F2 button also. Right. So this is the waveform I got. Now I have to change the input output ports names. So see here, input port name also net, output port name also in net. So these two ports should not be same name. So for that reason, click here. And if you want to edit this name of this port, then click on Q. Otherwise, give the right click. So I have given the right click. So see here, edit object option is there and the shortcut button Q is there. You have to select this component and type Q. Otherwise, click on this edit object. A window will come here. Okay. So here, here we have it at the downside net name. In this net name, click here and see here, net name I am typing in. Here I have typed in. So I have typed in and now I'm clicking on OK. Now see here, my input port name got changed. Next, click on this output port name and in your keyboard press Q. You will get this window and now type here out. Okay, now click on OK. So my input name got changed to, my input port got changed to name as in and output name got changed to E. Okay, right. Now the input name is ready, output name is ready, VDD is ready, and ground is ready. Now coming to our PMOS transistor. So our PMOS transistor also I have selected. Now I'm pressing Q. So this is the edit object window. Here I have length button, length option, width option. The length is I'm using here 0.13 U, that is 0.13 micrometer technology, or we can call this as 130 nanometer technology. In this video, we are drawing the CMOS designs by using 130 nanometer technology. And coming to here width, right? This width I am making very close to this length, right? So this is the width value I have given, right? The width you have to give more than the length. Length, if you are giving 0.13 micrometer, you have to give some 2 times or 3 times or 4 times higher than the length to width. So I'm giving the width value 4 times to the length, 4 times to the length, right? Now I have given 4 times of the width. Here you have some more options also. You can use all these options when you are designing deeply in this Mentor graphics. So I'm preparing this video for the starting who are starting freshly this Mentor graphics video. Okay, now I'm clicking on OK. Now CMOS also I'm changing. Click on the CMOS transistor, N-type CMOS transistor, and click here Q. Now you can change the value of NMOS transistor width also. Now this is 0.52 mu. So now click on OK. Right? All the value I have fixed here. All the value I have fixed here. You can see all the arrangements we did. Now we have designed correctly or not. You have to check and save. So see here at the top side, at the place of here the bars, at the toolbar, see here check and save option is there, and here save option is there. So click on check and save. So now click on check and save. So see here 0 errors are there. No, there is no errors. There is no errors. Only warnings. Warnings you can neglect. Only you have to check for errors. So this is with this we have completed the first step, that is creation of schematic diagram for your CMOS logic. Right? We have drawn the schematic diagram for CMOS inverter. Now the next step, second step is creation of symbol. Creation of symbol. Now go to the first file, edit, add. Add is there. So click on this add button and go to the generate symbol option. Generate symbol option is there. So click on this generate symbol option. Now you got a small pop-up window. In this First, you have to select replace existing. If any other person is created an inverter symbol, we are replacing that symbol, and whichever the symbol we are creating now, we are activating. These two options you have to select. First two, these two you should be click on OK. Next, you have to choose the shape of symbol. Which type of symbol you want to generate for inverter? You want any box or any other parameter? So click on the choose shape. Click on the choose shape. Which type of symbol you want? AND gate type symbol? No. OR gate type symbol? No. XOR type symbol? No. Buffer type symbol? Right. Yes. That is seems to be like as a buffer. Exact symbols are not available from these tools. So we have to take some similar symbol and you have to change by using which are the tools are available in this software. Now I am selecting buffer and click on OK. Now again click on OK. So see here, I got a window. I got a new window with a inverter symbol, right? It's not inverter symbol, it's a buffer symbol. Okay, this is the buffer symbol. Okay, now actually, if you want to make this buffer symbol as an inverter, you have to place a small circle at the end of this buffer. So for that reason, I want to move these two values. See here, I am moving this line and rhombus symbol, right? Now I want to place a small circle here. Left side, you can see lines, squares, rectangles, arcs, circles, text. All these details are available. So click on this circle, and here you have to create a small circle here. So this is the circle. Now this symbol seems to be like as an inverter. Now you have to save this one and check. So check and save, I have used it again, and now you have to close. So check and save, I did. So the report, there is no errors. Okay, so this is my symbol. Now close these two windows. So we created the symbol and we created the schematics. Now I am closing this complete window. Okay, let us see our cells are created or not and symbols are created or not. So this is your project. Under your project, you have inverter library. In this inverter library, one cell is there, inverter underscore sim. And here we have one symbol. Here we have inverter schematic diagram is there, symbol is there. So double click on this one, you will get a symbol. Okay, we got symbol. Now double click on this exact symbol. So this is your symbol. Okay, this is your symbol. Okay, right. These two are created. With this, we have created the first step of schematic diagram drawing. Second one, creation of the symbol. Okay, right. Okay, our next step to create a simulation circuit, right? So for inverter, we created the symbol circuit. Now we have to simulate that symbol by using a simulation circuit. For that, we have to create a new library, a new cell. So for creation of new cell, we need a library. So we have already inverter library. In this library, I'm giving the right click and go to the new schematic. So I am giving the cell name and schematic name as inv_sim, where SIM stands for simulation purpose. So you can take any of this name. Now I'm taking this inv_sim. Right. Now click on this one. Right. We got that schematic window, pixel schematic window. Now we have to call our generated inverter symbol. For that, you have to use add instance button. So click on this add instance button. In that, select inverter. In that, select the inverter underscore SYM cell. So this is the cell I am selecting and I am clicking on OK. So when I clicked on OK, I got the inverter symbol. So click the inverter symbol. Here, how many symbols you want, you can place. Here for simulation purpose, for verifying the functionality of the inverter purpose, I am taking only one inverter. Okay, right. Now I have to give the input and outputs for this symbol. So again, go to the port selection plane. So this is the add port in and add port out. Two options are available. So first click add port in and place here. Now go for add port out. Select here and place here. So we are placed one input port and one output port. Now here I have to give some input at this inverter like 0, 1, 0, 1, 0, 1 like that. So whatever the input you are giving at the input side of the inverter, you will get the inverted output at the inverter. So for that, I'm going to the library here. In this library, I'm going to the generic library. Here I'm taking ground and I am placing here first. One more ground I am taking for supplying the VDD. I have taken one more, and VDD symbol also I am taking here. I have placed the inverter symbol, the VDD symbol here. Next, I am taking some sources. So click on the source button and take some DC supply and place here. This is the DC supply. And one more we have to give either pulse or pattern. Here for a simple easy of operation, I am taking the pattern symbol. Okay, these all are the components I required. So I have taken two grounds and I have taken one pattern input and I have taken one DC input. So the DC input I am fixing for 1.8 volts. Okay, so select this one and edit the object name, object voltage values here. So here I am giving 1.8 volts for the DC supply. So here in the 130 nanometer based CMOS circuits, the 1.8 volts is more than enough. Next, so the remaining wire connectivity also we have to give. And output terminals also we have to connect here. So I made the connections. Right. Now the input port, I am changing the name. Edit object. And this is I am writing as in. Click on OK. And for this output terminal also, edit object, and the net name I am taking as an out. Click on OK. So this is the corrections we made. These are the connections we made for the simulation circuit. Okay, for an inverter. Now all the inputs I have given, right? Here DC voltage I have given as 1.8 volts, and at the pattern side I have to give again 1.58 volts only here. So here VHI, so low level logic is 0, high level logic is here we have 1.5 volts that I am changing to 1.8. Then click on OK. Right. So these are the modifications I did in the pattern and DC magnitude supply. And remaining, I have taken one input, one output, and inverter symbol. So the circuit is ready. Now go check and save. So click on check and save. There is no errors, only one warning. So leave the warnings, bother about the errors. So here we don't have any errors. Now click on the simulation button, which is there at the palette area. So this is called palette area, and this is called message area. In this area, this is called message area. Now go to the simulation option. So I'm clicking on the simulation button. Now it is asking enter. Now we are entering into the simulation mode. Click on the new design configuration and take any something file name. So I have given some not G, and here we are using ELDO simulation type. We are using ELDO simulation type. We are not using ADMS or ADAT. We are taking ELDO simulation type and click on OK. Right. So here for the design configuration, we have created a design configuration file. Name is not G, and the default simulation is ELDO simulation tool. Okay. Now click on OK. Now it will enter into the simulation mode. So see here in this simulation mode, we don't have any grid representation. In the schematic drawing mode, you can see the grid. So the grid is used for the easily placing the components. So for that reason, here now we don't have any grid in the simulation mode. And in the simulation mode, you have to remember one point: don't change any component values or names in the simulation mode. If you want to change any values, so here press end simulation button, then now you can change. In the grid mode, you can change whatever the values you want to change, but don't change the values in the simulation mode. There may be cause to some mistakes. Okay. So after entering into the simulation mode, here we have 4 steps. First one, we have to do analysis. Second step, we have to select the outputs. Third step, we have to do the run LDO operation. And fourth step, we have to see the waveforms. So first step is analysis. Second step is output selection. Third step is run LDO. And fourth step is view waves. So go to the first step, analysis part. So I clicked here, analysis button. So in this analysis button, here we have different types of options: DC analysis, AC analysis, transient analysis, and some SST, AC, SST noise, different types of analysis are available. So most of the times for the digital circuits, we have DC analysis and transient analysis. So first click on the DC analysis. At the DC analysis, here we have the sweep type option. So go to here and select a source here. Okay, sweep type, I'm taking source. The source I am selecting from the diagram by using this selection tool. So see here I have selection tool here. Which type of source I have in the screen I am selecting by using this plus button. So click on this plus button and we have to select our source as V2. So see here our V2 source is there. Click here. Then automatically that name will appear here. Automatically that name will appear here. Now coming to that source has minimum voltage 0 and stop voltage is 1.8 volts and step voltage is 0.1. These are the values we are giving in the DC analysis part. Now you have to click on apply. Don't click on the OK and run button. Our analysis setup is not yet finished. So for that reason, you have to select the apply button. Next, coming to more transient analysis. So see here, transient analysis option is there here. So here we are starting 0 nanoseconds to, right? How much waveform you want to see, right? How much waveform you want to see. For example, on the x-axis, I am taking either 300 nanoseconds or 500 nanoseconds. The time duration you have to provide with the start time and stop time values in the transient analysis. So my start time is 0 and my stop time is some, I am giving 400 nanoseconds. Interval, if you want, you can give, otherwise leave it. Generally, you can take 5 nanoseconds. Okay, 5 nanoseconds you can take, otherwise leave it 0, right? Then click on again apply. Don't click on the OK and run. So here we have selected 2 analysis. First one is DC, second one is transient analysis. After clicking the apply, close this window. So first thing, we have prepared analysis. Which type of analysis we are going to do here? That is DC analysis, transient analysis. Now come to the outputs button. So before clicking the output button, first select which is the input, which is the output. So this is the input button and this is the output button. These 2 wires you have to select at a time with the help of control button. So first select a wire with mouse click, then use the control button and select the second one also. Now click on the outputs tab. So here click the outputs tab. Now see here, input and output terminals I have selected from the schematic. These are the selections we made from the schematic. So for these 2 inputs, I am drawing which type of analysis. Here I have to select that analysis. First DC analysis. Here I'm plotting this DC analysis. I'm not saving. So for that reason, I have to define the task. In this task, I have to select plot. Plot operation, I have to select and click on add. Right. So see here some of the objects are added. So first probe sin is there. In this, I am doing DC analysis. The DC analysis I am doing for the input and output terminals of the inverter. Again, you have to select in. Again, you have to select out. Here, you have to select this time the analysis part we are taking with the transient analysis. So select the analysis of transient and click on add. Now the two input and output terminals are added here with the transient analysis. These two things we have to make here and click on apply. So what are the analysis we are taken? That is the first step, analysis part. Second step, we are selecting the outputs, which are the outputs, and for that outputs, which type of analysis we are making. These all are the things we have to select. And the task is very, very important. You have to plot. Right, output selection also completed. Now close this setup of the simulation window. Now coming to that, we have to run this schematic diagram, right? The simulation circuit we have to run with the help of LDO, run LDO tool. So click on run LDO tool. When you are clicking on this run LDO tool, you have to get the successful message in the message area. So see here, netlist is completed successfully and simulation is completed successfully. This message is appears in the message area. This is message area window. So this is very, very important. After completion of simulation, then go to the view waves. So now click on the view waves tab. So here I'm clicking the view waves tab. So I got these two windows. So that is wave 1 and next one is wave 2. These two windows I got here. So coming to here, in this wave, I have both input and output terminals are available. Both are overlapped, right? Now I want to split these two signals. We can select these two signals at a time and you can use a split option. Otherwise, you can select any one of the signal and you have to drag to the downside of the scale, right? So these are the input and output waveforms. These two are the input and output waveforms of the inverter. So this is the inverter input and this is the inverter output signal. So when the input is 0, output is 1. When the input is 1, output is 0. If input is 0, output is 1, 1, 0. So these are the combinations we got. So the maximum voltage here you can see 1.8 volts in the Y direction. And coming to the X direction, I selected 400 nanoseconds. So it is starting from the 0 nanoseconds and it is ended with the 400 nanoseconds. In this way, you can see the output waveforms, right? So these are the DC analysis. Now coming to the transient analysis. So here wave 1 is there. In this wave 1, you can see the transient analysis where the x-axis we are representing as the input voltage and y-axis we are representing as the output voltage. So input voltage 0 to 1.8 is there. Output voltage also 0 to 1.8 volts is available. Okay, right. So coming to see here, the input voltage is linearly increasing. Here, the input curve you can see here, linearly it is increasing. Coming to that output curve, you can see when in between the 0 to some 0.6 volts up to 0 to 0.6 volts, the output wave is in the stable state. That is, the output stage is logic 1. So after 0.6 volts, it is going to be down. Okay, when you observe after 0.8 volts, the output of this inverter is staying at the logic 0 condition. So this is the transient analysis. So here we have completed DC analysis and the transient analysis. And you can take this one as a printout. If you want, you can give the titles also. So here for example, in this waveform, use the right click and select the row title. So type here the input waveform. Okay, select here and click on OK. So you will get input waveform here name. right? Give the right click on this input waveform and select the properties. You can select the font size. So the maximum font size is 20. You can select 20. So like this, you can name the your input and output signals. Okay, you can select the size, you can select the text, whatever the things you can add. If you want to add for your signal, you can add, right, by the help of row title option. Then now if you want to take printout, right, select here the printout button. So print command here it is available. Select the print command. Next, see here, default I have taken as PDF writer option is there, PDF writer, and this is the command name where I have to save. So browse this button and select one location. For example, I am selecting the home folder. In this home folder YT12, this is our project name. At this place I am selecting to save my file. So here I am giving inverter 1. I have given inverter 1. Now click on save. Okay, next coming to that page setup. So in this page setup, you can see which type of wave you want to save, with white background or with color background, with black color signals or colorful signals. So whatever the purpose you require, you can place here. You can take the username, time, date, and you can see some of the advanced options like color displayed. You can save the waveform as is. Otherwise, you can save the waveform with black and white, white background and black color signals. Then click on OK. Now click on OK. You can select the landscape, portrait, right, visibility of waveforms, all waveforms, like that. You have multiple options. Now I have clicked on OK. Let us see the waveform is saved in that particular location or not. Now we will see. So go to places, go to home folder. In this home folder, we have created YT12, not this home folder. Go to the computer, file system, home, right, YT12 is there. In this, we have saved one PDF file, inverter1.pdf. So open this one. So see here, we can save the waveform in the landscape mode or portrait mode. So with white color background and black color text and black color waveform, you can see here clearly. So this is the saving your work at the end of the simulation. So with this, we have completed the simulation part. Okay, so with this, we have completed the first step of drawing the schematic diagram and generating the symbol. This is the second step. Third step, for that symbol, we are generated the simulation circuit. Why we created the simulation? Why we created the symbol? So why we created the simulation symbol? For this, the answer for this is for further use, for future, if you want this type of signal multiple times, then you can use this one. Okay, now all my output waveforms and all my simulation modes, everything is saved. Whenever you want, you can call, you can retrieve easily these waveforms and you can select. Okay, the use of symbol creation is you can use your schematic diagram in future. How many times you required, that many number of times you can use this symbol. Okay, most of the digital circuits are coming with the inverter and OR gates, otherwise NAND gates, NOR gates. Okay, so we are using these basic symbols or logic gates multiple number of times. Okay, so this is about the schematic diagram design by using CMOS logic, and we have seen the analysis part. Okay, simulation completed, and we have completed the diagrams part also. Right. In the next video, we will see the layout diagrams concept. Okay, thank you.